Computers are an essential part of architectural design. With the help of CAD tools and CNC software, we can construct forms that would otherwise be much harder to achieve. But in the early stages of a project, designers often prefer to work physically. They create tangible, low-fidelity prototypes. They want to know how people will interact with their designs in the real world, although since they often work in miniature, this is sometimes tough to see. Our research forms a link between this physical prototyping practice and the larger digital manufacturing pipeline. We introduce a room-scale mesh surface. It can be hand-sculpted into multiple forms, but simultaneously, it stores a digital copy of its physical geometry. Designers are able to experiment with a variety of concepts, interact with real-world objects, and then transition seamlessly to their software environment of choice. Here's a practical example. A library is undergoing a renovation, and the architects want to get some local input on what to do with the space. They bring in some participants from the community and let them use the mesh to create and explore different alternatives. The community decides that they want a seating area, and they use the mesh to sculpt one, grabbing real-world objects to use as references. They can create aesthetically pleasing forms, but also investigate practical concerns. For example, this wavy pattern looked nice from a distance, but in practice, it bulges out too far. This person makes an adjustment. A digital copy of the design is automatically generated. Our system senses the lengths of each mesh edge and then reconstructs the overall geometry through a dynamic relaxation routine. With the mesh now in software, the architects can post-process the form, create toolpaths for fabrication, and ultimately construct the room-scale feature that the community designed. The overall shape and the adjustments are both reflected in the final piece. Our mesh is composed of adjustable length beams, which we call T-modules. A user can expand, contract, or bend the module, and we can approximate the curve by detecting the length of the inner and outer strips. These flexible strips are made from FR4, and they're patterned with a resistive code. We read this code using a scanning head located at the base of the T-module. An onboard microcontroller then sends this data to an external computer. We use an energy minimization approach to reconstruct the mesh geometry from individual edge lengths. First, we obtain a coarse approximation of the structure, treating the mesh members as rigid links. We then reconstruct the curvature. Each T-module is represented as a polyline. We minimize the length energy at each line segment, a coplanarity energy at each module vertex, an axial bending energy along the polyline, and a transverse bending energy between module endpoints. Our system is designed to be modular and extensible, which can allow for future exploration of alternate geometries and topologies.